Thank you very much for for inviting me to this seminar. Between India and France. So my apologies for not being there, but I'm actually teaching outside France, so I was not able to come back today. So I will try to in this half an hour to share with you some of the activities that I have been doing with my group and collaborators on kind of evolution of reconfigurable intelligent surfaces or holographic MIMO, which we call stacked intelligent metasurfaces, and is a new idea that merges together, if you want, the powerfulness of metamaterials in terms of processing electromagnetic waves and the architecture, if you want, from the computing point of view of machine learning, more precisely deep neural networks. So and I will try to show you what there is around and what we are doing in this context, which it seems to be a very interesting research topics with many opportunities for research. So the idea, the main concept that I want to bring to you, I didn't add a lot of math, but I really want to share with you the ideas and some results, is how to do machine learning in the electromagnetic domain. So we are used to typical machine learning algorithms that operate in the digital domain, but how can we do something similar working directly on the electromagnetic waves? So what does it mean and what exists? So in simple terms, the main concept that I want to bring to you is that we know this structure, we are familiar with this architecture. We have an input layer where we send, for example, an image through a deep neural network, which is made of many layers, many neurons. They process the signals, and then at the output we want to infer whether what kind of image it is, for example, to make it in very simple terms. Now we know that the input of this structure is a digital representation of the image. Okay, what happens if we don't do any digital analog to digital conversion of the image and we try to implement all this in the electromagnetic domain? Okay, whether this is possible or not. So the technology to do that is the programmable metasurface, programmable metamaterial. So the main idea is that each layer of this deep neural network that you have, each hidden layer, can be viewed as a metasurface, and each neuron of this metasurface is one tiny antenna element that is capable of processing the signals. Okay, that's essentially the fundamental idea. I want to show you what exists in this context, what we can, if this is possible, what kind of applications we can have in wireless communications, and then I will show you some results in order to justify the reason why we are looking for multi-layer structures and the differences with conventional RIS. That I've seen that there are many presentations in these days, so I'm not going to go much into the basics of reconfigurable intelligent surfaces. So now for the in this talk I will take, at least for the numerical results, a very simple model for this metamaterial. So I will consider, I guess, as in many presentations that you have seen or you will see, that each element, each neuron, if you want, operates as a simple phase shifter. We can do much more than that, but just assume that each element operates in this way, just for the sake of simplicity today. Of course, if we claim that this is done in the electromagnetic domain, we should use more consistent electromagnetic models, but that's maybe we discuss towards the end. So now, first of all, I claimed at the beginning of this presentation that we want to do this in the wave domain, okay? Machine learning in the wave domain, or DNN in the wave domain, to be more precise. So now, is that new? Is that not new? Which is the starting point? So, this concept of realizing an analog neural network processor, it's something that dates back to some years ago. I cannot really tell you whether this is the first paper. It's certainly one of the first papers, but we are still trying to search deeply on the literature, but here you can see some people who have contributed a lot in any case to machine learning, where a few years ago, it's 1991, there was already the idea of merging together digital processing with analog processing because doing everything in analog reduces the complexity, reduces the power consumption. So there is something to gain, and this was one of the architecture that basically these people proposed, where you can see multiple layers, where in part, I mean, they were implemented in the digital domain, and in part they were implemented in the analog domain. More recently, there was a revival of this technique, especially in the optical domain. So for those of you who are working on RIS and especially electromagnetic aspects, you may know that most of the models have been initially proposed in optics, and then we adapted them to our domain. This is a paper published in Science in 2018, where people propose what they call an all-optical machine learning based on diffractive deep neural networks. And the idea is again that of reducing the complexity and the power consumption of these devices. So now, how does it look like? Essentially, you have many layers of optical materials, as you can see here, and this signal, you illuminate the first layer through an optical emitter, and then the signal goes through, is processed through these layers, and then at the output you observe your image, for example, and you can infer, for example, what kind of digit there is in this image, or whether the image is something else, or what there is in the image. And there is a clear connection between the electronic neural network, so what we call neural network, where all the connections and all the processing is in the digital domain, and on the other end, there is optical processing. Okay, so this is one of the papers where this was proposed. In this paper, the architecture is not reconfigurable, so it's a static. What does it mean? It means that it's like if you are utilizing, if I go back, a metamaterial. This was done in optics, okay, but you can think of a metamaterial where there are no electronic circuits. So you design it, you make it once, and then you cannot change it. Okay. Then a few years later, in 2020, okay, let me skip this. In 2022, another group from China generalized basically this approach that I proposed in 2018 in Science, in a paper published in Nature Electronics, where they proposed a programmable AI machine. So it's essentially a diffractive deep neural network, which is active, that basically is also basically reconfigurable. The only problem of this device is that, as you can see here, it modifies the amplitude, and so is an active device. So it introduces some amplifications, which is not exactly what we want to do with RIS, for example, because you know that one of the main features of reconfigurable intelligent surfaces is the claim that you don't use power amplifiers and you make it as simple as possible. So there was an evolution from something that was not reconfigurable, it's something that is reconfigurable, but with power amplifications. So the concept is there, but still it was a little bit different from what we see in the wireless community or in the RIS community. In any case, there is an hardware platform that does this, that is able to, for example, take an image and then process this image and try to recognize what kind of image this is. This is the kind of hardware that you can see with the multiple layers that interact, and they work 100% in the electromagnetic domain. So the proof of concept exists, and then I will show you also some experiments that we did with some collaborators. So this structure, in practice, if you want to have an idea, and then I go to more system concept, but is basically multi-layer of programmable devices. For you to know, these devices look like very similar to what people are utilizing for RIS, with the only difference is that you don't modulate the phase, but you modulate the amplitude. But essentially you have multiple layers, the signal goes through them, and then you surround this device with some absorbing materials to avoid that the signal goes anywhere. That's the way that it works. So it's a proof of concept, it's not a device that you can sell at the moment, but I mean the principle is there, and there is some possibilities that is going to be further developed. So now, this is what exists. So now, just to give you an idea of the fact that this research field is highly interdisciplinary, most of the research works, we will find them in science, nature, and in the field of optics. Okay, and there are also some implementations in not in optics. So in wireless communications, we called this technology, then I will try to clarify it a little bit better, we call it stacked intelligent metasurface. I will try to give you a brief introduction to it, what kind of performance you can get, 3 main applications without going much into the math, and then I will show you some experimental results, 4 applications to communication and sensing and their integration. So the idea is not to really go much into the mathematics, but rather to give you an idea of how it works, what gains you can get, and then of course if you have questions, I would be happy to go into the mathematical details. So now, so what is this SIM? So this SIM is essentially a multiple reconfigurable metasurfaces, one stacked one after the other, which don't work in the reflection mode like many RIS devices that you may be familiar with, but in transmission modes. So you illuminate the first layer, and then the signal propagates from layer 1 to layer 2, from layer 2 to layer 3, like a feed-forward deep neural network. So the idea is that you do have, each layer is made by a programmable metasurface, so unit cells plus electronic circuits, but we don't want to use power amplifiers, we don't want to amplify the signal, so we retain the fact that we just want to work on phase shift, like those that you are familiar with for RIS, but not in reflection mode, in transmission mode. So, and therefore, I mean, you can clearly understand that we are really trying to mimic this, as I told you at the very beginning. So now, why do we want to use this structure? There are 3 main applications that I want to show you for applications to wireless, and then I will show you the corresponding results in the second part. So, application number 1, we want to use this in order to realize beamforming in the wave domain rather than in the digital domain. What are the pros and cons? So this is a typical base station that you can think of, where we have a baseband digital processing, then we have a high resolution digital to analog converters, and then we send the signals through the antennas. You can have an hybrid implementation with some phase shifters if you don't want to have a number of RF chains which coincide with the number of radiating elements. But long story short, what you want to do with this deep diffractive neural network or SIM in wireless communications is that you want to avoid baseband processing. As you can see here, you don't have this digital processing anymore. You want to have a simple digital to analog converters. Then you fire the signal and you put just after your antennas this structure, this multi-layer device, and you process the signals in the EM domain at this stage. So essentially you are removing this baseband processing and moving this baseband processing after the antennas and do everything in the analog domain. That's essentially the principle. And you could also do something more sophisticated, which I like more, where you have your antenna feeds directly connected to the first layer, and then you add multiple layers, you stack multiple layers after the other. So this is a more long-term implementation. This is a more short-term implementations, which could be deployed just putting this panel in front of your antenna, multiple panels in front. Now, why this makes sense, at least, I mean, would make sense, because we know that most of the power consumption comes from the analog to digital conversion. So, essentially, the power consumption increases exponentially with the number of bits that you use. And also, if you move up in frequency, like millimeter wave, sub-terahertz, also it increases linearly with the bandwidth. So, you would like to reduce somehow this power consumption. And if you move to analog, you don't have these bits anymore. That's one of the main motivation from the practical. Then there is also, this is the first application. This second application is to utilize the multi-layer structure for improving the performance of metamaterial assisted wireless. So let me give you a concrete example. So we are used to utilizing these metamaterials in reflection mode. But you can also use this metamaterial in transmission. What does it mean? You could put these metamaterials on a window, and you could enable communication between outdoor and indoor. You could put this metamaterial on a wall and facilitate the propagation of the signal between one room and another room. Okay. So now let's consider that we don't have only one layer, but we have multiple layers, and they work in transmission mode. Okay. So now, the typical RIS or metasurface structure that you are familiar with is what we call diagonal structure. The diagonal structure means that each antenna element that we have on this surface is controlled independently. We have an impedance that controls the reflection or transmission coefficient of each antenna element independently. Mathematically speaking, this is a diagonal matrix, which characterizes the reflection or transmission coefficient depending on whether you are using a RIS reflecting or a RIS in terms of refracting, so transmitting. Now, information theory, I'm not going to give you the proof, but information theory tells us that the best, the information-theoretic optimal structure should be not diagonal. It should be a full matrix. This in communication is known as beyond diagonal RIS. I think that many of you are working on that. But there is an increase of complexity. Move from this to this, it's a huge increase of complexity, power consumption of the circuits, and so on and so forth. So you achieve the optimality from the information-theoretic point of view, but at the cost of complexity, power consumption, etc. Now, the details of the proof of the information-theoretic functionality you can find in this paper. There's also another paper published by other authors, but I skip these mathematical details today. What the concept that I want to bring to you, that I want to convey to you, is that a SIM, a multi-layer structure, would be utilized in order to approximate a full matrix, a beyond diagonal matrix, with the cascade of diagonal metasurfaces. So let me go into the details. Imagine that you have one layer, and then you have another layer, and the signal propagates from one layer to another. Each layer has a diagonal response, first layer and second layer. What do you have? You have that your end-to-end channel is given by the product of the transmission coefficient of the first layer, with the transmission coefficient of the second layer, and the propagation matrix from layer 1 to layer 2. So, if your layer has a diagonal response, you have a diagonal matrix here, T1, a diagonal TL-1, a diagonal response TL, but in the middle, you have a propagation matrix which is full. So your end-to-end matrix has a non-diagonal structure. So you are mimicking a full, an end-to-end matrix of propagation inside this device by utilizing diagonal metasurfaces. So you can keep the complexity of each device simple and stacking them together. Okay. This could be realized in practice, and I will show you applications to wireless as well. So this is the second application. The third application, before seeing the results, is the one that I find most exciting, which is viewing this SIM as a computing platform, okay, in the electromagnetic domain. So what is the idea? The idea is that you may have an input signal that propagates through this multi-layer structure, and at the output you could do some operations. This is called in jargon really basically this is something like performing mathematical operations directly with the metamaterials. Okay, so this is one paper published in Science by some colleagues. Where, for example, in this illustration they show that you could take a signal, the signal goes through it, and then at the output you can get the first order derivative, the second order derivative of the signal, or something like that. So to do really wave domain computing, okay, electromagnetic computing. Now, the example that I will show you in the numerical results in a few slides is that we utilized the same principle, SIM, to compute the bidimensional discrete Fourier transform of the input signal, because this has many applications for example, correction of arrival estimation or for integrated sensing and communications, which I will show you. The concept is, imagine that you want to compute the DFT. the DFT of a signal will be characterized by a matrix. So if you take this matrix and you multiply it with the input signal, you get the output is the DFT of the input. Okay. If you want to do that in the electromagnetic domain with a SIM, what you would like to do? You write your end-to-end response of the SIM through the cascaded product of all these matrices. Okay. Then the input signal X goes through this G, matrix G, and at the output you get R. If you want that R is, for example, you want that R is the DFT, what you should do is essentially to make sure that G is equal to F. So if you optimize your transmission coefficient in each layer such that G matches F, okay, in principle your R should be the DFT of the input, because we are matching this matrix with what happens when the signal propagates through the SIM. That's essentially the idea. So in principle you could build any function by solving a minimization problem which matches the end-to-end response of the SIM with the actual response that you want to obtain according to some mathematical models, mathematical operations. Okay. So now I want to give you some numerical examples for these 3 case studies very, very quickly. I will give you the problem formulation and the results without going much into the algorithmic design, but if you are interested, I'm happy to discuss and to share with you the papers. So the first example that I showed you is to use a base station, is to mimic a base station, but a base station that does recoding in the wave domain. So the system model that we consider is the one that I already showed you. You have just low resolution DACs. You don't do anything in the digital domain. The signal is fired by the antennas. This distraction is close in the near field to the transmitting antennas. The signal goes through them, and then you want to serve multiple users. So the problem that we want to solve is similar. First of all, the signal model that we use for the propagation between the layers is this model here, which is called the Rayleigh-Sommerfeld diffraction model. Essentially, we take into account that the propagation between the layers is in the near field. Okay, this scalar model is quite simple, but for what we want to do now, it's sufficient to show at least whether it works or not. Okay? That's just to give you an idea of how we model the interlayer propagation. The problem that we want to solve can be formulated in this way. It's the canonical one for multi-user systems. So we want to maximize the sum rate. We model the interference as noise, so we model everything as a signal to interference plus noise ratio for each link. The matrix G, I've already showed it to you. Our optimization variables are the phase shift of the transmission coefficient. We assume ideally that the amplitude of the transmission coefficient is equal to 1, which is a perfect scenario, which is a starting point. It's not realistic, okay, but it's a starting point to do the analysis. So we solve this problem by using the gradient descent technique. I skip these details. The results that we get is the sum rate as a function of the number of RF chains. In blue, you have the solution, fully digital solution. In red, you have what you get with the SIM. Here you have 4 RF chains, let's say 49 or 100 scattering elements on each layer with 7 layers. And you can see that if the number of RF chains is the same for both structures, zero force beamforming, conventional one, and the SIM, you can get a quite good improvement of the rate, because you capitalize on the nearly passive scattering elements on the device, while the RF chains are exactly the same. Okay, so that's one of the gains. It's a sort of a similar gain that you get in an hybrid holographic MIMO structure, but it's pretty significant here also because of the multi-layers. The second example that I want to show you is the usefulness of multiple layers in order to shape your radiation pattern in a very accurate manner. So imagine that you have this multi-layer device, and then you want to create this pattern. This is a spatial pattern, okay? How the power is distributed in space in a given region. Imagine that, for example, here you have a street, and you want to make sure that you are able to illuminate that street with a good amount of power, and then you don't want to have a leakage outside that area in order to make sure that your efficiency is very good. Well, what in principle you need to do, is to optimize the go back, is you optimize the transmission coefficient through the layer, so always this matrix G, such that the amount of power that is observed in each square here is exactly the same as your target. So again, you need to solve a minimization problem that matches this pattern to the optimization of the transmission coefficient here. Okay, we solved this optimization problem by using the gradient ascent algorithm in this case, and the results are the following. You can see that with only one layer, you don't have sufficient optimization variables in order to give you this accurate resolution. When you increase the number of layers, you can see that you can get much better performance. This is one layer, this is 3 layers, 5 layers, and so on and so forth. As the number of layers increases, of course, there is a diminishing retard law, but I mean, already 3, 5 layers, I mean, maybe 7 is the best, but I mean, with already a few layers, you can get something good. So the multi-layer structure really helps you in utilizing simple layers implementation and then capitalizing on this cascaded effect that you're going to have. The third example, which is actually the most interesting for me, is really trying to estimate the direction of arrival. So I need to close in 5 minutes, so I go a little bit faster. But the idea is that imagine that you have a signal that comes from a given direction and a plane wave that illuminates this structure. You input this signal, which is sensed by the first layer through this SIM, and then you observe the amount of power that you receive at the output of this multi-layer structure at different observation points. If you can compute the DFT of the input signal, the DFT gives you, observed at each point at the output, the amount of power that you receive, that might be received from different directions. So there is only one probe point in which the amount of power is really big, and on the other end, all the others, ideally, in the absence of noise and interference, they should be ideally zero. So you have what is called the angular spectrum, so the distribution of power for all possible angles of arrival So the proposal, I skip some mathematical details, but the proposal says that you observe the amount of power at each observing point, and then you take the index, which you get the max power. And then you can go back from that index to the actual angles that from which the wave comes from. Okay, so we implemented this, and these are the results. So this is for 16 probes that we deployed. These are actually the different angles, phi x and phi y, and here you have the digital implementation with typical algorithms that you can use, and here on the other end you have what you can do with SIM, and you can see that they are not much dissimilar, and also the accuracy is not that bad. In red there is the actual angle of arrival, and this is the map of the estimation accuracy at the different observation points. Okay, so it's pretty good. I mean, at least as an initial proof of concept validation. This is only with numerical simulations. Now I close with only showing you that this device, there are people actually working on that. So this is one results obtained in collaboration with some researchers at this university in China. So I don't do anything, no hardware implementation in my lab at Central Saclay, but I'm basically collaborating with these people, and the connection was established thanks to two students who graduated from Central Saclay, and then they went back to China, and then they established basically this connection between me and this university. So they did the experiments. So the idea is that this is each layer that they built is one metasurface where you have multiple tiny antenna elements. Each antenna elements can introduce two phase shift, 0 and 180 degrees. So extremely simple. This is the structure of the unit cell, which we have pin diodes that control the reconfigurability. And long story short, this is just a snapshot of the testbed that they used for validation. At the moment, this is working at 5.8 GHz, so sub 6, and they tested from 1 layer to 3 layers. Okay, so the results are the following. This is communication oriented, where you can see this is the amount of power that you receive when you have 1 layer, 2 layers and 3 layers, and when this is the distance between the layers, okay? Lambda over 4, lambda over 2, lambda, and so on and so forth. First of all, you can see that this system is not always working well, in the sense that you can see that from 1 layer to 3 layers, you receive the power could also decrease, not necessarily increase. We notice that this increase when the distance between the layers is less than lambda over 2. So when the layers are very close to one another, because you reduce the insertion losses, etc. So it's a system that in principle should work very much in the near field, and so it's very difficult to be optimized. The optimization of this device is at the moment done almost completely by brute force, so we are now trying to do something better, but at the moment the idea was just to show that in principle it could work, okay, without even applying amplifications, power amplification. So, and the gain is not that bad. And this is another example where you do direction of arrival estimation. So what we did is the following. Actually, this slide, you have a transmitter, you can move the transmitter at different locations, and the idea is to infer, to estimate the direction of arrival based on the signal that is observed. Okay, that's essentially the idea. And also in this case, here we consider only the root case. You can see that there is a decrease of the estimation error as the number of layers increases. Okay, so in principle, there are many, I would say, many papers that have shown some gains by using very simple mathematical models. This is one of the first where we can really see some experiments, and so there is still a lot to be understood, but at least it's a proof of concept that it shows that if you optimize the system, you may get some gains through this multi-layer structure, even though the devices are not ideal. That's essentially the main things that we can get, but there is much more to be done. Okay, so that's just an initial and preliminary result. So now this will be presented at Globecom. Now we are working on the journal paper, so there are still a few things that needs to be improved. And then if you wanna have more information about this, these are some of the documents that I utilized for this presentation that are not the only papers available. I just wanna tell you that is a pretty recent research topic. The first papers, at least in wireless communications, they were published in 2023. In beginning 2023, we published a paper at SEC 2023 for application to multi-user beamforming, and so it's pretty recent. And so there is much more, opportunities for research than for other like RIS, etc. I don't have time. I just want to stop here, but I want to tell you that we are about to finalize one paper where we try to establish this historical connection between these different fields and between neural networks, electromagnetic computing, and the metamaterials, or what is called the generalized refraction law, and so on and so forth, moving towards SIM. So this should be available in the next few days. Online. So if you are interested, we can discuss. And the last thing that I want to tell you that I will not discuss is that there is now also an interest in going from planar metasurfaces to essentially conformal metasurfaces. So metasurfaces that are not necessarily planar, but that they could take different shapes. Okay. And this is because there are metamaterials that allows you to do that. This could also be added in conjunction with the SIM, because if you have, if you can bend your substrate, you could also optimize this. If I go back, in principle, you would also optimize this coefficient W, because depending on how you bend the signal, you change the propagation characteristics between the layers. So this gives you another extra degrees of freedom for optimizing this system. Of course, the complexity is getting huge, but that's the direction where we are trying to go to. And in any case, we have already shown that by optimizing appropriately the locations of the antennas, you can get some gains. Okay, so but the combination of flexible conformal surfaces with SIM does not exist, to the best of my knowledge. I'm not aware of papers that are available currently online. So if you want to know more, these are two papers which you may have a look at. The first one is still under the review process. We submitted recently the revised paper. The second one, Tetris, is already accepted and is available on transactional wireless. So you may want to have a look if you are interested in this conformal metamaterials. That being said, I stop here. Sorry, again, for not being there physically, but I truly appreciated the opportunity to share with you this research. And if you have questions, I'm happy to respond and to discuss. So thanks a lot.
Long live India and France friendship.